Welcome to Not Factory Approved. Today is going to be a little bit of a departure, well, actually a big departure from what I've done previously. Today I'm going to be dealing with some electronics in the form of a power supply and some test equipment and drawing schematics. And after that, I'll be showing how to test and maybe revitalize Nicad batteries. Stay tuned. Hope you enjoy.
Well, it's been about a year since I worked on this HP power supply. It's a power supply I'd really like to get going. The main beauty it has is that it's controllable up to 60 volts, 6 amps. So you can current limit it or you can voltage limit it. It's really handy for checking batteries, like small drill batteries and so on, and individual cells. So last time, by my notes, I've changed these two. And I think I powered it up after that and it failed within a few seconds. Unfortunately, my notes don't say that. I might have just packed it up in frustration. In the final steps, I know I replaced those two. One, because they're socketed. Two, because I remember. I do have this device here, which is a Huntron tracker. Now, these are really useful if you've got two boards. One is good and one is bad. But they can give some useful information. They give some curves depending on whether you're checking a capacitor or an inductor or just plain loading of a circuit. It's a graphical indication of what's going on. And you can also change the size of the pulses that are given to it and the frequency. I'm going to change tack slightly. Hewlett-Packard used to make test equipment and medical equipment and analytical lab equipment, mass spectrometers and gas spectrometers and so on. My first job was with Hewlett-Packard Medical as a biomed. When I first became a biomed, they were my first employer. But with the test equipment, they have all the manuals online. Unfortunately, the old manuals, like this for this unit, were hand scanned, put into a large file and available online. So whoever scanned this one really didn't care, and I can't really blame them because they're probably doing hundreds of thousands of pages with all the equipment. You can barely make out some of the detail, but these ones are completely obliterated. There's nothing I can do about that. I have it on the computer, but I just can't enhance the image enough to get any kind of detail out of it. So I am redrawing that section using what I know about the chips and can find online on data sheets. And then what few details I have of where pins go. Then I will see if I can get it to make any sense in that block, and maybe I can find out what's causing these ICs to blow. Wish me luck. Now here's the moment of truth. It's coming back to me now. I spent a bunch of time on it previously, and then it failed after a few seconds for the second time, and then I changed both chips and I ran out of time, so I put it away. It's been up on the shelf for almost a year, so now I will turn it on. I was scoping things out and wasn't finding a problem, so see what happens here. Okay, it's coming up with the display. So on control voltage now. So you set the voltage up. I've got no load on it, so there's no current. It never lasted that long before. So I think what was happening was the trigger flip-flop for the protection had a shorted input. And it was blowing the clock circuit that drove it. When I changed the two of them, it seems to be okay. So now I'll start putting some loads on it, see what happens. So apparently I gave up on this thing way too early. Could have had this working a year ago. I didn't do anything today other than look, try and draw some schematics, test a few junctions, turned it on, it works fine. So I actually had it fixed a year ago, but I just gave up. Such is life. Anyway, I've got it going into basically 100 ohms now. If I put it on control voltage, I can set it up higher. There we go. Well, I'll show you current then. But control the current. There we go. Just reset. Okay, so I can control the current. I haven't seen that problem before. It must be because it was so low on the current. So there's 0.1, just under 12 volts. Put it to voltage. I'll just disconnect, let it reset. Get back up. And 12 volts, a little bit higher current. So I put it to current limit, and then the voltage drops because I'm lowering the current. So perfect. Put it all together. Now I can check all my drill batteries that are over in here. See which ones have bad cells and which. When you lose a hard drive, it can create all sorts of long-lasting issues. So started this project about 1.5 years ago, and of course most of that video is gone, unrecoverable, even though I've tried many different ways to get the disk to work. So this here, I'll start from the scratch. I bought this years ago at an auction at a electronics manufacturing plant, and it had failed. I bought it for $15 in the auction. It's a multi-$1,000 power supply at that time, and the problem turned out to be that the encoder, which is in here, that controls voltage and current settings. Right now it's on voltage control. There's a little light bulb in there. It goes through a slit wheel, and that bulb was burnt. So I replaced the bulb. I didn't use an LED because at that time high intensity LEDs were quite expensive and hard to find. Believe it or not, it's going back about 20 years at this point. So that's what I did, and for a few cents I fixed it. Well, then it went into storage for 2.5 years when we moved, and I used it one day after unpacking it, and then it quit. So it took me quite a while to get it fixed. And I'll tell you what, one of the beautiful things about Hewlett-Packard equipment is you can still get schematics and service information. HP used to be a wonderful company that made test equipment, computers, printers, chemical analysis equipment like gas spectrometers, mass spectrometers, made medical equipment. They all had different branches, and instruments. And this is from the instrument branch. Great equipment, often very complex, but reliable and high performance, which is what they used as an acronym for HP. So this particular power supply, this is the control section. I know it looks quite complex. This is the power supply section, 0 to 60 volts and up to 6 amps you can supply. Now this sat for a while, and it was fairly old, so when it failed, just on as part of preventative stopping future problems while I was troubleshooting it, I replaced some of the capacitors. I had most of them, and I bought some others. It wasn't highly expensive, but the old ones were pretty dry, I think, so just to save any problems during troubleshooting, I replaced those. Then I went to work trying to find out what was wrong with it. The schematics for this particular one have most of the detail, but they also were hand scanned. And the time they were hand scanned, it was single sheet and then putting everything into a file. So it was a very time-consuming process that HP did to get their manuals online. Something I'm very appreciative of. Now, if you find old HP equipment at auction and you have any kind of electronics knowledge, don't hesitate to buy it, I would say. I worked for them for 5 years as well, and they're an excellent company to work for. But back to the problems. So this is the display and control board as far as setting voltage and current, done through the encoder here, which goes through this cable and into the board. So there were two ICs that were bad, those two that are in sockets now. One is a flip-flop and one is a 3-input and logic gate. So the flip-flop had a shorted input, and that blew out the AND gate. So it couldn't get its drive signal to operate the power supply. As far as it had a 320 kilohertz square wave that ran the oscillator, and that was stepped down to 20 kilohertz. That's 20,000 cycles per second. And so it couldn't operate. It took me quite a while to find that. And I actually had this fixed quite a while ago, but I didn't know it because I ran out of time. Last ditch effort before I put it away. I replaced both these ICs, put them on sockets, and then I ran out of time. So I put it up on the shelf, closed it up, and waited for another day. And when I started troubleshooting it again, I found out I had actually fixed it about a year ago. Oh, one thing a power supply like this is good for is checking batteries.
Oh, nice.
I'm checking the drill batteries and I'll sort out which ones are good and which ones aren't. So with these cells, which are nickel cadmium, Nicads, they can be checked by putting a current of around 1 amp in and seeing what happens to the voltage. So I've current limited this to 1 amp, and then the voltage should climb up. What I did was I set it for a voltage of 1.35, which is a typical charge voltage for a nickel cadmium single cell, and then I see how it responds. This one did go up to 0.5 volts and then it dropped down again, which is a sign that it's no good. It's not going to recover. It will never have any real capacity to it. Now you can do this with a regular power supply or maybe even a battery charger if it's decent quality. And then you can, so you need a DC voltage basically, not one that's varying all over the place with lots of AC on it, which a cheap battery charger would have. So I'll just move through the cells and I'll isolate. If I find any good ones, I'll take them out and then I'll throw the rest away or recycle. But you can do this with a regular power supply that has not got current limiting by putting a resistor and then checking the voltage across it. Across the resistor you would get the exact current that's going in, and you could set it up that way and watch what happens to the voltage on the cell with a digital meter or analog too if you've got one. So this is what I'll do, and we'll see what happens with this thing. So there's the first cell. Always make sure you've got the right polarity. So now this is positive here. Set onto that. Well, let's try there. Okay, 2.4, staying pretty stable, so likely that cell's no good either. Sometimes you can bake them and get some heat in there if you put in 2 amps, but that's a last ditch effort. And sometimes you can break down the oxides that are inside the cell by putting a lot of current through it. But never would do that with a good cell, just ones that are on the way out. Sometimes you can bring them back that way. So let the testing continue. This may be a bad cell. I will check. It started off with very low current up to the voltage, so it might be open. This one started with a high current, and the voltage jumped up quite quickly, and then the current started dropping. That's a sign that it's a good cell. It took a charge quickly. But if it takes it too quick, then it's open. And this one has not really changed much, so I'm thinking it's probably open. But I'll go through and check the others. The first pack I did, all the cells were bad, and none of them responded to a charge. So I'm just going to try this whole pack at once, see if I can get it to respond. So what I'm going to do is, it's an 18 volt pack, so I'm giving it roughly 10% more. That's the charge voltage. I'll put it over to current, and we'll see what happens. Zippity doo-dah. So now I got to go through and find out which cells are bad. So this is what you want to see with a good cell. I'm going across two cells now, so I just don't have to take it out of the pack. So it starts off, the current is high, and then it starts dropping. Initially it went from around 1.5 volts and jumped up fairly quickly to 2.7, and then the current started dropping after that. So that indicates it's taking a charge, which is a good sign. There it is, climbing.
At least there's a few glimmers of intelligence.
Putting 1.5 amps into it, watching it climb. 18 volt pack. Once it gets up to 20 volts, it should start dropping. So this one looks like it may have some good batteries in it, like all of them. The initial problem was that one of the wires that I had put in before, because I had replaced all these batteries, had shorted. So one cell was getting charge voltage. One cell was being shorted by this wire. So the pack got hot and the wire melted, and of course it wouldn't charge after that. We're still climbing. And they're starting to heat up now. I think some of the oxides inside, crystals, are starting to break down. So I can use these to fix some of my 19.2 packs. I'm not going to bother with the 18 volts. So the 19.2 drills are much more powerful. The reason I'm using a higher current is to just try and shock it into taking a charge. There we go. Now this should start dropping. There it goes. Keep an eye on it for heat. Make sure the cells don't get too hot. They're all perfectly fine. I'll just let it charge for a bit. And then I'll get on to there's another 18 volt pack to go through, and then I'll go into the 19.2s. So the bad news for today is that my power supply quit, ran for about 6 hours, and then stopped. Good news is I got a couple of the batteries working. They're rejuvenated a bit, so we'll see. 2 of them were dead. One would not turn the drill at all, and one was just extremely weak. It would run down within 2 minutes very easily. So I cannot stop it now, which before was no problem at all. So, see how they do. Ouch. This one too. I can't stop it. Burns my hand. So that's some good news for today anyway. As I was saying before, the people who scanned these, they didn't pay a lot of attention on some of the models. But these are overlapping pages, but you can see the blocks are pretty indistinguishable. So what I did find was that if I changed it to reverse, it was a little clearer. This is the same circuit there. And if I shone a light brightly on it with a magnifying glass, I could actually look inside some of the blocks which are indistinguishable, like here, for instance. You can hardly see what's in there, but here it's much more obvious. So that did help. And then I was able to sort out some of the circuitry. There's also a good block diagram of the power supply. So this shows power input. Then there's some filtering. There's a rectifier. And that's a secondary transformer, or secondary voltage supply. Then you have driver transistors here, which drive these MOSFETs, metal oxide semiconductor field effect transistors. See, there's no connection between the conducting channel and what's called the gate. This is called the source, and this is called the drain. And I'm not going to get into electron theory, it's all just going to confuse you. So basically, we're looking at it like this is the supply and current flow is this way. And physics says it's different than that, but that's the way electronics works. That sets up a 20 kilohertz oscillation, which drives this transformer. You get two separate rectification, and it changes, usually pulse width modulation, and that's controlled with a feedback loop. The area where I was having the trouble was in here, in the feedback loop. It was not allowing it to drive. It was shutting off these transistors, so it wasn't driving the MOSFETs, so no output. Once I replaced those two, it worked fine. Now the problem I have is after 6 hours of use, these MOSFETs shorted, and whatever other damage there is, blew a fuse, burned up some resistors. So one day I'll get back to that. I do have the parts now. Problem is that you can't get direct replacements for these anymore. I can find no information on them at all, so I have to run with assumptions. Like 300 volts maximum and 6 amps maximum, even though it will be less than that, because this is the primary side, the voltage is getting stepped down. So it would be more current on this side, less current on this side. So what I got was some 250 volt MOSFETs with 6 amps maximum. And I'll have to modify everything because there's a different case structure. You can't get the TO3, which is the larger case, anymore. So I went with the best I could get. Stay tuned for that one. But that's the basic theory of the power supply. And the power supply working side looks like that inside the case. These are the two transistors, or MOSFETs rather, that drive the power supply switching mode. And that's about it for now. The other board that's in there is for HPIB control, which is Hewlett-Packard instrument bus. And they could tie all of their test equipment together, so you could get test routines running. So it could be automated test, and that's not something I'm ever going to use. So half of the power supply is of no use to me. But this part certainly is of use, and it's a very high quality power supply. So I hope that helps. I hope it's of some interest. Once I changed the black and white to opposite, then I was, and the bright light on it with a magnifying glass, I was able to draw out the circuit. It's incomplete, but that's the basic idea. It's feeding back. You got an overvoltage protect, you got an AC dropout protect. There's a clamp, control voltage clamp, so that's checking whatever you've set it for, and that's determining whether it will pass the 20 kilohertz signal or not through this gate. And there's the flip-flop. So those two, that's the same, oh sorry, U10A, U9B, and U7A. I had problems with these two. That was what stopped it from working initially. Hope you enjoy.
Please don't forget to like, share, subscribe, or even notify, or any of the above, or all of the above. Thank you.